This video will introduce you to case control studies and binomial probability. Case control studies examine exposures between those who become ill, who are known as cases, and those who do not become ill, known as controls. Case control studies look back in time when the outbreak is already known. The outcome is people becoming ill. Let's take a look at an example of when a case control study might be used. Let's say Mr. and Mrs. Smith are happy newlyweds who had a beautiful wedding with a catered buffet dinner. And the next morning, two attendees of the wedding wake up and begin experiencing diarrhea. At first, it was chalked up to too much champagne, and then it was discovered that others were sick, even those who did not partake in the bubbly. The mother of the bride catches wind of the illnesses and decides to call the local health department to report it. She's upset because she paid good money for that caterer and never expected everyone to get sick. Health department employees begin talking to wedding employees about what they ate at the wedding, obtaining menus and contact information for those who were sick. They ask about leftover food items to test, but unfortunately there was nothing left over from the wedding, so no clear food item is becoming apparent as the source of the outbreak. They are able to obtain stool samples for a couple of cases, and those are pending at the state lab. And environmental health goes to the catering company to do an inspection, and they are able to obtain a list of the food items provided for this event. A case control study is appropriate at this point because it's an outbreak with no clear indication of a vehicle. But first, you have to create your case definition so you'll be able to differentiate your cases from your controls. Case definitions include clinical features and person, place, and time. In this outbreak, a case will be defined as an attendee of the Smith wedding on October 15th who became ill with diarrhea or vomiting within 48 hours of wedding attendance. Next, you want to pick your controls. Conversely, a control comes from the same population, so it will be a wedding attendee who did not become ill after attending the Smith wedding on October 15th. When you're picking controls, it is important to remember that controls must be comparable to the cases in the sense that both groups would not be at risk if there were no disease exposure association. This means we wouldn't want to have controls that only apples are susceptible to. We wouldn't want to have controls with a disease that only apples are susceptible to and use oranges as a control. Or controls who are all immunocompromised if none of the cases are. And we wouldn't want to have children as controls if all of the cases are adults. For those of you who have dealt with an outbreak like what's happened at the Smith wedding, you are aware that tracking down guest lists and attempting to speak to both sick and well persons can be a little bit like herding cats. It can be difficult to ensure that you're reaching all of the wedding guests, which is really important. When reporting results of a case control study, your statistical power, or how reliable your results are, increases with the number of cases and controls that you have. So how do you find controls? First of all, keep all of your cats on leashes, but after that, you can ask if there are any of these options available that might help locate controls. So social media, email lists, guest lists, meal companions, using credit card receipts, or even reaching out into the community to find friends or neighbors who are applicable to the control group. As you may know or might find, it can be really difficult to convince people who aren't sick that you want to find out what they ate or didn't eat at the defined location during a case control study. It is really important to obtain information from both sick and well persons, as it's the only way that you're able to paint a broad picture of the outbreak. There will likely be healthy people who did eat the contaminated food item, but there will likely be more sick people than well people in that situation. It can take a little bit of finesse to get healthy people to talk. When it comes time to create your case control study, this is the time to go against what you were taught in elementary school about cheating from your neighbor. We do not suggest starting your survey from scratch. There are many examples available from other counties, states, food safety centers of excellence, and CDC. Don't forget to add fields that capture demographic data. You can also use a catering or food prep menu to ensure that you capture all of the foods and drinks that are available to guests. And don't forget that sometimes food comes from multiple cooks, so ask about all of the places that the food came from. And as with the survey, it's important how you analyze your data as you're creating the survey. Next, you want to think about how you send your survey. The quickest and most cost-effective ways to send surveys is through a service like SurveyMonkey or Qualtrics, and recruit participants via email or social media. However, this can be pretty indirect and hard to get a response. You can also attempt these over the phone, which can be burdensome depending on how many people you need to call. Face-to-face is also an option, but this is less likely considering the burden on most health jurisdictions. Again, case control studies compare the frequency of the exposures in the case group to the control group by asking about what everyone, those who became ill and those who did not become ill, were exposed to during a time frame of interest. During a case control study, we would ask whether cases and controls consume certain food items, hopefully to be able to determine the food item, the exposure, that is most highly associated with becoming sick. Once the interviews are completed, it's time to look at the data to come up with a measure of association. The measure of association that comes out of a case control study is called an odds ratio. It tells us the relationship between an exposure, such as eating ice cream, and disease. In simpler terms, how much higher are the odds of exposure to a certain food item in cases as compared to controls? This is called a 2 by 2 table, and it's what's used to calculate odds ratios. The table has 4 fields, A, B, C, and D. A is the number of sick cases who are exposed to the item of interest, which in this case is ice cream. B is the number of well controls who are exposed to ice cream. C is the number of cases who did not eat ice cream, and D is the number of controls who did eat ice cream. With some simple math, we can obtain an odds ratio. The equation calculates the odds that a case was exposed, or A divided by C, divided by the odds that the control was exposed, or B divided by D. Or more simply, A times D divided by B times C. In this case, the math gives you an odds ratio of 19.6. When we're interpreting the odds ratio, here's how to understand them. An odds ratio of 1 would mean there's no association with illness and the vehicle of interest, or ice cream has nothing to do with becoming ill. An odds ratio of more than 1 would mean the exposure of interest is associated with becoming ill. This would mean that ice cream is associated with illness. Finally, your odds ratio of less than 1 means that the exposure to the vehicle of interest is actually protective against becoming ill. This means that eating ice cream would protect you from becoming sick, and this, my friends, is what dreams are made of. Another way to interpret the odds ratio is by understanding what this would mean for your cases versus your controls. If the odds ratio is 1, then the risk of becoming ill after eating ice cream is the same between cases and controls. If the odds ratio is above 1, then there's a greater risk of becoming ill with the exposure of interest. This would mean that those who ate ice cream are almost 20 times as likely to become ill after eating that ice cream. If it is below 1, then those who ate ice cream are almost 20 times less likely to become ill. Now, the other part of the odds ratio includes p-values and confidence intervals. And if you're anything like me, then you understand what I mean when I say that these words are pretty scary. When we talk about confidence intervals and p-values, we're operating on the idea of the null hypothesis. The null hypothesis is based on the idea that you're working with a large population, known as the source population, where the incidence of disease is the same for everyone, both those who are exposed and unexposed. With this, the assumption is that the exposure is not related to the disease. Remember that when you're trying to disprove your statistical calculations. You want to show that the null hypothesis, which says that there is no association between exposure and illness, is wrong, and that there is an association between exposure and illness. In this case, the null hypothesis says eating ice cream has nothing to do with becoming ill. When you reject the null hypothesis, you're trying to prove that the alternative hypothesis is correct, that there is an association between exposure and illness. In this case, we're trying to prove that eating ice cream does have an influence on whether or not someone becomes ill. When you see the p-value, you should think probability. And we want a small p-value because the small p-value means that we'd be very unlikely to observe such an association if the null hypothesis were true. The p-value tells us the probability that eating ice cream is unrelated to becoming ill. So back to our odds ratio of 19.6. With this odds ratio calculation, we got a p-value of less than less than 0.0001, and a confidence interval of 11.1 to 34.5. In the upcoming slides, we'll talk about what this means. We've used our exposure data from the CaseControl study to determine that the odds ratio of becoming ill are 19.6 times higher if you ate ice cream. But how do we know whether this is reliable? When we have a small p-value, typically 0.5 or less, we get to reject the null hypothesis. And if we reject the null hypothesis, then we accept the alternative hypothesis, which says that eating ice cream is associated with disease, and those who ate it were more likely to become sick than those who didn't. We often see that statistics include what's called a confidence interval, and it is usually accompanied by 95%. It is a range of values, in this case, 11.1 to 34.5. And this range of values should contain the Q, which in this case is 19.6, or our odds ratio. So this confidence interval is telling us that if we ran these statistics 100 times, 95 of those 100 times we get an outcome that included our true value, which is our odds ratio. So what we can remember here is that a wider confidence interval indicates large variability or imprecision, and a narrower confidence interval indicates less variability and greater precision. So we always want a more narrow confidence interval. Another way to think of this is to use a gambling analogy. The odds ratio tells us which number to bet on. The confidence interval tells us how much money to bet. You would want to bet more on a narrow, more reliable confidence interval than a wider, less reliable confidence interval. The take-home message is, it wasn't safe to eat ice cream this time. With an odds ratio of 19.6, a very low p-value, and a fairly narrow confidence interval that it contained our odds ratio, it's safe to say that the association of ice cream and illness is not due to chance alone, and that ice cream was indeed associated with illness, so much so that those ate ice cream were almost 20 times as likely to become sick as those who did not eat ice cream. Now I want to discuss the use of binomial probability, which can sometimes be a way to determine the need for conducting a case control study and can also be a great tool for hypothesis generation. This is Jacob Bernoulli, a Swiss mathematician who was born in 1655. He's responsible for the Bernoulli trials, or binomial probability, which is a tool that can be used by epidemiologists to generate hypotheses and can be an alternative to case control studies. There are times when you have a suspicion of what the food item was, but you don't have the resources to complete a case control study. Or perhaps you have multiple food items that are suspicious, but you aren't sure which hypothesis to follow. These are both times that are great to use binomial probability. Binomial probability can be used to help you gauge whether the number of cases you have who have consumed a certain food item is what you'd expect under normal circumstances. This complex calculation is what's happening during a binomial probability trial, and lucky for you, there's a very handy spreadsheet that will magically do these calculations for you. This is the number of possible outcomes when you're doing a binomial probability calculation. In most cases, it will be eaten or not eaten, attended or not attended, yes or no. To use the spreadsheet, you need a few pieces of information. You need to know how many people in your sample, meaning the number of cases or sick people in your study, and your background rate, which is the percentage of people you would expect to have the exposure of interest in the general population. You can obtain the number of cases with a certain exposure from your epi data. But then we have to find out what our background rate is. What percentage of the population would we expect to have exposure to ice cream or shrimp or potato chips during a given time frame? So an easy resource is the FoodNet Population Survey Atlas of Exposures, which is seen here. So let's look at some data using a Maricopa County outbreak of shrimp at a seafood restaurant. A case control study was used in this outbreak and found that unfried shrimp was a likely source of salmonella. So we'll use this to perform our binomial probability. The case control study found that the food item most often eaten by cases was unfried shrimp. Once a case control study was completed, they found an odds ratio of 6.7. meaning those who ate unfried shrimp were 6.7 times more likely to become sick than those who did not eat shrimp. With binomial probability, you only need data from the cases, not the controls. In this instance, we know that there were 21 people sick and that 17 of those people ate unfried shrimp. For a binomial probability spreadsheet, we'll use the number 21 as our sample size, which is 17 plus 4. As far as the background rate, we'll take a peek at two sources. So the FoodNet Population Survey shows that about 28% of Americans would expect to eat shrimp within the past 7 days. The Arizona Food, Animal, and Water Exposure Survey, or FAWS data, is another resource available to you, and it shows that about 22% of Arizonans ate shrimp in the past week. Now, obviously, these sources do not specify whether the shrimp is fried or unfried, which is typically important during this investigation, but because unfried shrimp was flagging. However, you typically can use this estimate and still obtain meaningful results. If we know that we have 21 cases of salmonella, and we'd expect a background rate of 28% of people to consume shrimp during any given time frame, but we see that 17 or 81% ate shrimp in this sample, we get a p-value of 0.0000, which tells us it's highly unlikely that we would see this association by chance alone. With this, if we had to place our bets on unfried shrimp, this would be a good one. Now, binomial probability doesn't work as well for commonly eaten foods like eggs, which FoodNet says that 88% of people ate in the past week. But it is very useful for less commonly eaten foods such as shrimp, like we just saw. Another consideration to make with the use of binomial probability is that it should never be used alone. Every investigation, whether binomial probability is used or not, should rely on multiple data sources. To finalize, depending on your outbreak, a case control study may or may not be indicated. Tacking on binomial probability is free and costs you nothing more than a few minutes. Each has its own pros and cons that should be weighed when deciding next steps in your investigation. As always, the food team is available to help or answer any questions that you might have. Thank you.